welcome everybody. This is session 14, timetabling and scheduling in pandemic applications. We've got 4 talks, and we're going to start right away with Richard Hoshino and Irene Fabris, partitioning students into cohorts during COVID-19. And so, Vienna, could you play the video, please?
It's actually live.
Oh, it's live. Oh, sorry. All right. So I guess Richard.
It's gonna be Irene.
Oh, it's Irene. Ah, okay. Go ahead, please.
Thank you, Chris. Hello and welcome, everyone. My name is Irene Fabris, and today I'm presenting our paper on school timetabling titled Partitioning Students into Cohorts During COVID-19. It's the first time I'm attending an academic conference in person, and it's an honor to speak to all of you today. I finished my undergraduate degree at Quest University Canada in April 2020, and this paper is an extension of my honor thesis in a joint work with Dr. Richard Hoshino. Here's the outline of my talk. I'll first introduce a new formulation for a school timetabling problem, which we call the Student Cohort Partitioning Problem, or SCPP. Then I'll model our problem as a 5-dimensional integer linear program. I'll then deploy our model at a Canadian high school, and I'll use 2 heuristics to find close to optimal solutions in just under a minute to conclude the talk thereafter. What motivated our work? Well, the outbreak of the COVID-19 pandemic forced academic institutions across the world to make significant changes to bring their students back to school safely. The Center for Disease Control suggested that the best measure for school administrations to take to ensure and reduce the spread of COVID is to ensure that students, the same group of students, would learn together, avoiding interactions from other student groups. We call these groups learning groups or cohorts. Now, the Canadian province of British Columbia, which is the province where my co-author and I reside, allowed schools to reopen in September 2020, provided school would partition their students into cohorts. But how does one create these cohorts or learning groups? Well, creating learning groups is easy at primary schools and elementary schools, and it's often easy at universities because students in business school don't take the same set of courses as students in mechanical engineering, for instance. However, in high school, where students register for a diverse set of courses from all disciplines, partitioning students into cohorts or learning groups is really hard because the students really want to get into their desired courses. The school timetabling problem, which is studied by many researchers at the conference, is known to be NP complete. In the next part of the talk, I'll explain how we extended the school timetabling problem to take learning groups into account. So let us define I, T, C, S, B, and L to be respectively the set of individual students, teachers, courses, sections, blocks, and learning groups. Notice that blocks are simply the time slots or time windows when courses take place, and learning groups are used here as synonyms of cohorts. Now, in 2007, Lewis et al., during the second international timetabling competition, introduced the formulation known as post-enrollment course timetabling problem, or PECTP. We defined the student cohort partitioning problem to be identical to the PECTP with 3 additional requirements. First, that each student is assigned to a learning group. Second, that each course section is assigned to a learning group. And third, that a student is enrolled in a course section during a learning group if and only if both that student and the course section belong to that learning group L. We also define course sections to be simply course offerings. For example, the course can be calculus and there's 5 sections of it. So we modeled our student cohort partitioning problem as a 0-1 integer linear program as follows. Let X, T as CBL be equal to 1 if teacher T is assigned to section S of course C in block P and learning group L, and is 0 otherwise. Similarly, let Y, I as CBL be equal to 1 if student I is assigned to section S of course C in block P and learning group L, and 0 otherwise. So our integer linear program aims to maximize this objective function, which is simply given by the sum of the variables X and Y multiplied by their respective weighted coefficients D and P, where D, TCB, is the desirability coefficient of assigning a teacher to a course in a block. And P, ICB, is the preference coefficient for assigning a student to a course in a block. Also notice that these two coefficients, D and P, are independent of sections and learning groups. Because, for instance, a music teacher will always be qualified to teach music classes, regardless of sections and learning groups. So our objective function is subject to multiple hard constraints. I'll give you a few examples. No teacher can teach the same course twice. Offer the right number of sections for every course. No student can take the same course twice, nor can a student be enrolled in multiple sections during the same block. Now, to account for learning groups, we also introduced two additional binary variables. We call them X hat and Y hat. Define X hat, SCL, to be equal to 1 if section X of course C is assigned to learning group L and is 0 otherwise. And lastly, define Y hat, IL, to be equal to 1 if student I is assigned to learning group L and is 0 otherwise. All in all, our objective function is subject to 11 hard constraints, 7 of which include the variables X and Y hat. And these remaining constraints are assign each student in each course section to exactly one learning group, assign each course section to exactly one teacher, assign a student to a course section during a learning group, as we said before, if and only if both the student and the course section belong to that learning group, and respect the maximum capacity for every course section and learning group. So how does it play out in reality? Well, in July 29th of last year, the British Columbia government mandated maximum cohort sizes of 120 students in high school. This created panic among high school principals who had just about 4 weeks to redesign their MasterCard timetables entirely before the beginning of the academic year, and to do so in a way that would partition students into learning groups so that each learning group would contain students that would allow them to enroll in their desired classes. Because school administrations and school administrators are usually not trained in constraint programming, artificial intelligence, and operations research, many students really suffered greatly from this policy. They were told that there were less course options and were registered into courses that they had no interest in taking. However, one school took a different approach. St. George's School, which is an all-boys high school in Vancouver, Canada, asked my co-author and I to find an optimal partition of the 328 senior students at the school into 3 learning groups to maximize the number of students getting into their desired courses. I just presented the model. We used the IOP to formulate and solve the student cohort partitioning problem. Now, this school runs a 4-day tumbling timetable comprising of 4 class periods and 1 lunch break every day. So they alternate between the blocks ABCD on days 1 and 3, and the blocks EFGH on days 2 and 4, repeating this pattern for the entire academic year. The school had also set some priority classes for courses, specifically required, high, medium, and low priority. For example, for us to register a student into a mandatory English course is more important than granting them their music elective class. We accounted for these priority classes by setting weights to the preference coefficients P. And specifically, we treated required courses as hard constraints, which you actually hard-coded in the integer linear program. And we then set 5, 3, and 1 points for high, medium, and low priority, respectively. So our job is of creating the timetable ultimately amounts to mapping course sections to blocks. Specifically, at this school, we had 328 senior students, about 50 teachers, 196 course sections, 8 blocks, and 3 learning groups. The administration at the school had pre-assigned each of the 196 course sections to 1 teacher qualified to teach that course. So this pre-assignment had actually reduced the problem size to just about 1.5 million binary variables. So when L is equal to 1 learning groups, and that's the standard and almost trivial case when there is not any forced partitioning of students into learning groups, then our program coded in Python using the MIP solver coin or branch and cut computes in just about 8 seconds, satisfying 96% of student course requests. In the majority of the 4% of the cases where students were not granted with their required or desired courses was simply due to course over-enrollment. For example, law studies had 66 seats available, but 78 students had requested it. So when L is equal to 1 learning group, virtually everyone got into their desired courses, provided courses were not oversubscribed. On the other hand, when L is equal to 3 learning groups, problem size increases alongside computing time. So we apply approximation algorithms. We apply 2 of them, a progressive assignment and a large neighborhood search. In the progressive assignment, we divided course sections into priority classes sorted by preference coefficient P. And then we solved the student cohort partitioning problem 1 priority class at a time. Specifically, we solved the student cohort partitioning problem for required courses first, which are just a small subset of all the courses in C. And we set the X variables found in the optimal output as hard constraints for the following step, when we solved the student cohort partitioning problem on the next priority class in order of priority, obviously high, then medium, then low. Throughout this process, the X hat variables remained fixed. However, we allowed for the Y and Y hat variables to change at each of the case step. This is because once the X hat assignments are set, our integer linear program quickly finds the optimal assignments of students to course section and learning groups in order to maximize our objective of enrolling students into their desired courses. In the large neighborhood search, on the other hand, we reshuffled variables to iteratively improve our solution. We picked an arbitrary initial solution. In our case, we decided to take the output of the progressive assignment, which we already knew to be close to optimal. We locked in all but H of the X hat variables, but by setting them as hard constraints. And then we re-executed our program to generate a new solution where H, many course sections, would be assigned to different and new learning groups, again, in order to maximize our objective of enrolling students into their desired courses. We ran each step for about 60 seconds, reshuffling H equals to 30 course sections. And in each trial we ran, the solution quickly converged to the same objective value. Here are the best results when we combine the 2 heuristics. The table comprises of 4 columns. The second one is the total amount of courses requested by students. And the third and fourth column is what we could attain by the progressive assignment and the large neighborhood search, respectively. So we were able to enroll students into 1,997 out of 2,303 total courses. This is 100% of the required courses and about 87% of the desired courses. Naturally, we wondered how close this implemented solution was to the optimal solution to this real life instance. And in our paper, we explain and show that our solution is at most 5% away from optimal. And we also show that our results are indeed optimal for the category of required and high priority courses. So in conclusion, in early August of 2020, St. George's School reached out to us, and 2 weeks later, we delivered their final master timetable, partitioning 328 students into 3 learning groups and satisfying 87% of their desired courses. It is actually in part thanks to our timetable that the school registered 0 COVID cases among staff and students at the senior school for the past academic year. My co-author and I were also hired by 5 new and different institutions in the province of British Columbia to design their master timetable for the academic year of 2021 and 2022. And St. George's is among them. This time we designed for them 2 timetables, one with L equal to 3 COVID-informed learning groups, and one with just L equal to 1 learning groups in a post-COVID scenario. Given the declining number of COVID cases in Canada and the world, we are optimistic that the school this time will be able to implement our L equal to 1 learning group timetable, which actually enrolled 99% of students into their desired courses. In the months to come, we look forward to continuing serving schools by designing their timetable using techniques in CP, AI, OR, and of course also testing our 2 heuristics on benchmark instances of the post-enrollment course timetabling problem. Thank you very much. I also would like to thank my co-author, Dr. Richard Hoshino, Quest University, Canada, and of course my family and my dad that is here today. Thank you so much.
All right, thank you, Irene. For some reason, I can't turn on my video, so I can't show up, but are there any questions? Here we go. Peter, you've got a question.
Yeah, it looks like you did random neighborhoods. Did you have you considered any other kind of neighborhoods to try to improve your solutions?
That's a really good question. So we did in a very informal way by actually choosing ourselves the 30 variables that we wanted to be reshuffled. We actually looked at the output and we selectively chose the courses that were dissatisfactory or that were really not granting many students to get into what they requested. And so we manually fixed that. I know it's not optimal, but it was a greedy manner to attain a close to optimal result given our upper bound, which we prove in the paper. We are really open to explore more non-random manners to guide our local search for sure. If you have suggestions, I'll be very, very open to listen to them and implementing them.
I think you need to formalize what you're doing by hand, right? Because you obviously have some insights as to what a good neighborhood is going to be. You need to understand what was your rule of thumb that you're using, and then you should have a good neighborhood, I guess.
That's totally right, yes. Especially given that we have a good problem knowledge of our instance, we did so, but if we want to scale it up, we would need to identify good neighborhoods in an algorithmic manner.
I see there's a question, Vienna.
Yes, thank you for your presentation. So maybe more not technical question. In these 2 weeks, how much you slept, and why you think it worked that you could reach solution for so short time?
Well, not much, but that's how it works with contract work. So we didn't sleep much. But the point of it is that last year, for instance, we were working on pre-processing using graph coloring. This year, we wanted to really get a deliverable ready by the deadline. And that's the reason that informed our design to get a working solution fast and then continue the search from there. Yes, does that answer the question? Yeah.
Okay, thank you.
Any other time for a quick question? So I have one. Can you talk about any feedback that you got from the schools about the timetables? Was there any interaction or anything that you got back from them?
Of course. Thank you so much for the question. This is actually a big portion of our work, the customer relationship. So when we program or design their timetable for this year, we took a slightly different approach. Our algorithm was partially the same. However, the feedback that we received is that we wanted to also improve the fairness metric. And so for this reason, the school had provided a set of a ranked set of alternative elective courses that each student wanted to get in. And so we had included it and also guaranteed that, for instance, 7 out of 9 of the course requests for every student were met, so that we were not only optimizing the cumulative total number of satisfied course requested, but the proportional number of course requested satisfied per student. But so far, it seems the interest is there. That's why it's the second time we are timetabling for them. It's the third year in a row that we are timetabling for the school that informed our research of last year, St. Margaret. So yeah, the partnership is going well, and we hope it continues. And we hope also to be able to expand just for research purposes, our heuristics design. Thank you for the question.
Thank you. I see there's one more question, and I know that I think the next talk is in Vienna. So maybe we can switch speakers and have that last question from Vienna.
Yeah, no, actually, it's interesting because I have a very similar question. I wanted to ask about fairness, and you have many optimal solutions. Maybe some are more preferred than others. It could be that even in the case we have like L is equal to 1, it still could be that one student like lost 2 of their preferences, for example, and maybe better if 2 students lost 1 of their preferences. But then we should lose it and stuff like in other questions, it's quite tricky.
So the model that you've seen today, the interdisciplinary program specifically, is quite simplistic, and there's many more constraints that we actually implemented when we sold the timetable to the school. One of them, for instance, is really a balancing constraint that is enforcing, again, a percentage of the request for every student to be satisfied, and we set them to a minimum to guarantee, fairness for each student, because the ultimate, the priority for the school, and ultimately we're serving a customer, is to maximize the cumulative number of requests. But again, it's also in the interest of the school to retain students. That's why we don't want to disadvantage one over the other. And that's easily implementable by just adding a constraint, which may be a bit costly, but overall not much.
Okay, great.
Thank you.
All right. Thank you, Irene.